How you deal with?
What is going on, everybody? It's your boy Average Leader here with another video, and today we are tackling number 269, Alien Dictionary. This question is commonly asked by Facebook, Amazon, Pinterest, Microsoft, Google, and Airbnb. If you guys can go ahead and hit that subscribe and like button, that would mean the world to me. It helps my channel out a ton by giving it more exposure to people that don't know me. And if you want to see another problem done, just comment down below and I'll make sure to do it for you. And with that all out of the way, here we go. There is a new alien language that uses the English alphabet. However, the order among the letters is unknown to you. You are given a list of strings words from the Alien Languages Dictionary, where the strings and words are sorted lexicographically by the rules of this new language. Okay, so we're given a string array, and we're given a bunch of words in this language, and supposedly the order of these words are in the order that makes sense to these aliens. Our job is to return a string of the unique letters in the new alien language sorted in lexicographically increasing order by the new language's rules. If there is no solution, return an empty string. If there are multiple solutions, return any of them. Okay, that's an interesting thing to note. A string S is lexicographically smaller than a string T if at the first letter where they differ, the letter in S comes before the letter T in the alien language. Okay, so let's just look at this example. Looking at the output, we have WE, and looking at our words, W here comes before E. So I guess another thing to note, we'll look at an example in just a second. And let's just look at this last bit. If the first min s.length, t.length letters are the same, then S is smaller if and only if the length of S is less than the length of T. Okay, this is an interesting problem. Let's try and look at a few examples on the iPad. Now, before we look at the alien language and the alien dictionary, let's just see if we can solve this problem using the English language. Now, our input dictionary is this list of words right here. And as of right now, we're just going to follow all of the English rules where A comes before B, B comes before C, A, B, C, D, E, F, G. You guys know the alphabet. So that's the rules that we're going to follow. Now, before we go any further, let's just remind ourselves that we're trying to return a string of letters. And let me just clarify a bit more. We're trying to return a string of unique letters sorted based off of the rules of the language. Now, in English, we know that this input is going to be sorted alphabetically. So in this particular example, with the letters that we have here, our output will be A, B, C, N, O, P, U, Z. And let's just double check that I didn't miss any letters. Okay, great, so I didn't. So we know that this will be the output. Now, the question really becomes, how can I utilize my input array to get this output right here? So let's just look at our input array and see if we can figure some stuff out. And let's also revisit the problem description. It specifically tells us a string S is lexicographically smaller than a string T if at the first letter where they differ, the letter in S comes before the letter in T in the language. So that's just all a fancy way of saying the way we know that Anne comes before Buzz is based off of the first letter that they differ. And we know that in the English alphabet, A comes before B. Now look at this. In these two words, where's the first position where they differ, the first index where they differ? Well, that is the 0th index. We see that A and B are different. So we know from here, A comes before B based off of these rules. And in the English alphabet, we also know that A comes before B. So let's just keep that in mind. Now, let's look at these two words, right? In which index are these two words different? We see that at the 0th index, once again, B and C are different. So Buzz comes before cop because of these two letters. B comes before C. So we also know that B comes before C. Now let's look at cop and cause, because this is an interesting one. They both have the same first two starting letters. So let's look at the first index where they differ, and that happens to be the second index, P and Z. So cop comes before cause because P comes before Z. Now we have a little bit more information that we didn't have before. And, so what are we going to do with the letters that we haven't used? Well, let's just hold on to the letters that we haven't used yet. So we have N, O, and U. Okay, so based off of the information that we have right here, let me see if I can make a connection to our information that we've just gained in our output string. So in our output string, I see that A comes right before B, and B comes right before C, and P comes right before Z. So looking at the output now, does this look familiar? Maybe if I redrew this information that we received in another interpretation, maybe you guys can see something that I'm seeing right now. Let's say we had A go to B, B goes to C, and then we have P here go to Z, and then we just had nodes N, O, and U. It kind of looks like a graph, doesn't it? And this output right here looks like the topological ordering of our graph. Now, for those of you who don't know what a topological ordering is, it's actually an ordering such that when we're given two vertices, and I'm just going to use A and B here, when we're given two vertices, A and B, and we have an edge from A going to B, in our ordering, A comes before B, and that's exactly what we have. And notice here, we also have B pointing to C. So where is B and C in our output? Well, B comes right before C. And let's also look at P and Z here, right? Where is P and Z in our output? Well, B, once again, comes right before Z. It doesn't matter if it's directly right before, it's not in the place of U here, but we know that in our ordering, P comes before Z at some point. So that is a topological ordering. And this actually makes the problem much easier. It's a little tricky to see that this is a graph problem, but I think only after I drew out this interpretation right here, this really helped me kind of picture that this is, in fact, a graph problem. So now we know that this is a graph problem. We know that we need to use topological sorting on our graph to get the output that we want. Maybe we can run this in an actual example, and we can even go through the whole topological sorting implementation. But before we go any further, if you guys are a little unfamiliar with topological sorting, I definitely recommend watching my course schedule 2 video, the implementation in depth, how to pick a problem, how to know when to use topological sorting. See, in this problem, I didn't even explain. Some hints that helped me figure out that we had to use a topological ordering here was, one, we have a graph. Like, we know that we can use a graph representation. So when I started making these arrows from A to B, B to C, I kind of realized that, okay, so we could potentially use a graph here, not sure, not 100% sure just yet, but then I realized that our input words that we have, these input words, they're essentially rules that we have to follow. And those two are actually some of the biggest hints that we can use to know that we have to use a topological sorting. If we have a graph, and if we have rules that essentially tell us that one node in the graph comes directly before another node. So in this case, and comes before buzz, and buzz comes before cop, and cop comes before cause. So that is essentially an ordering that we must follow. So those are some of the key things that I was looking for in this problem that helped me realize that we need to do a topological sort. Let's actually try this on an example that was given to us from Leetcode. So I'm going to go to our example. So this was the exact problem that was given to us on Leetcode for this problem. So let's basically run through this problem. We know that we need to represent this input as a graph somehow, and we need to run a topological sort on that graph. So let's go ahead and try to figure out how we can do that. So based off of what we just did in the first example, and the example that we did earlier, we know that we need to construct a graph somehow using the letters in here. And the way we did that was comparing two words at a time and checking to see what exactly makes one word come before the word right after it. So in our situation, let's look at WRT and WRF. According to this alien language, they are telling us that WRT comes before WRF in this language. Now, what letters actually make WRT come before WRF? Well, it has to be this T and F. We know, based off of this information, that F is going to come after T. Let's compare the next two words. The aliens are telling us WRF comes before ER. So what makes WRF come before ER? Well, it has to be the W coming before the E here. So we know that W comes before E. Now let's look at the next two inputs. We have ER and ET. Now the aliens, once again, they're telling us ER comes before ETT. What exactly makes ER come before ETT? Well, it's not the E's because, you know, those are the same. Those aren't going to give us information. But we know that R here is coming before T in this situation. So let's add that to our graph. R will point to T. And finally, let's look at the last pair, ETT and RFF. The aliens have told us ETT comes right before RFTT. Sorry, guys. I know that looks like an H. Let me change that. Sorry about that. T. Okay, so aliens told us this information. How exactly does ETT come before RFTT? Well, it's because E in this situation comes right before R here. So we have this information that E comes right before R. Now, we've essentially constructed our graph here. This is our graph. It's very simple, but a graph nonetheless. Now, let's go ahead and run a topological sort algorithm on our graph. And for those of you guys who've seen my course schedule 2 video, you know that I really like using an in-degree in our implementation for topological sort. So let's have the nodes that we have represented in our graph, and let's have an in-degree of each of those nodes. And just really quickly, for those of you guys who don't know what an in-degree is, when you have, let's just say node A pointing to node B, an in-degree of a node represents the number of directed edges that go into that node. So when we look at B here, B has one directed edge going towards it. Hence, it has an in-degree of 1. A has nothing going towards it, no edge going towards it, so it has an in-degree of 0. This is a very quick example. I explained it a little bit more in that video, in the course schedule 2 video. So let's go ahead and write all of our nodes that are in our input. So we have T, F, W, E, and R. And I also want to bring up a good point here. In our situation, we're very lucky that all of the unique letters showed up in our graph here. But let's just say in our last word here, we had RFTTA. All right, so essentially we had RFTTA. Now, even though there's not an edge that goes directly into A, or A doesn't point to anything, it's still in our graph. And the way we'd represent that is we just let it be its own letter. So if we were looking at this from like a graph representation, it would look something like this. So you can see that W goes to E, E goes to R goes to T, T goes to F, and A would just be its own node on the side. So A, I just want to make it very clear that A is still represented in our graph. Just because there's not an edge going into it or out of it doesn't mean that we don't, you know, keep account of that, because we need to make sure that A is in our output string. So the only way we can make sure that it's in our output string is to also make sure that it's represented in our graph and in our in-degree somehow. So just keep that in mind, guys. So now let's go back to our example and let's figure out what the in-degrees are for each of our nodes. So if we see node T, we see that there's one edge going from R to T. So hence, there's one directed edge going into T. The in-degree of T is 1. Now let's look at F. F, there's one directed edge going into F. So the in-degree of F is 1. Now W, I don't see W anywhere on this side, so that means there's no directed edges going into W. I see the first time W appears is right here. There's no edge going right into W, so W has an in-degree of 0. Now let's look at E. E is right here. There's one edge going into E, so E has an in-degree of 1. Now let's look at R. R is right here. R has one directed edge going into it, so R has an in-degree of 1. Okay, so now we have our nodes, we have the in-degree of all our nodes, and now let's just go through the basic topological sort implementation. I'm just gonna look at what I had from my course schedule 2 video, and I'm just gonna explain real quick. So the first thing we need to do is find all the vertices with an in-degree of 0 and add it to a queue. Next, we're going to remove all nodes with an in-degree of 0, and we're also going to remove its outgoing edges from the graph. Now we're going to reassign the in-degrees of the nodes that were affected, and we're just going to redo these 3 steps over and over again until we have 0 nodes left into the graph. So let's just use the graph that we have up here. Now also, whenever we find a node with an in-degree of 0, let's go ahead and put it into our output string. So I'll just have output here. And let's go ahead and begin our topological sort. So let's find any node that has an in-degree of 0. We see here that W has an in-degree of 0. Let's go ahead and add it to our output. And let's remove it from the graph and its outgoing edges. So W is right here, and let's remove it and its outgoing edge. So now after that, we need to reassign the in-degrees of all the nodes that were affected. We see that E used to have a directed edge going into it. Now it doesn't. So now it has an in-degree of 0. So let's go ahead and change E's in-degree to 0. And now let's restart the process. Let's find all the vertices with an in-degree of 0. Now we see that E has an in-degree of 0. Let's add it to our output string. And let's remove E as well as its outgoing edges from the graph. So let's remove this and this and this. Now let's look for all the nodes that were affected. We see that R is the only node here without a directed edge going into it anymore. So let's go ahead and change the in-degree of R to 0. And now let's go ahead and restart the process. What are all the nodes that have an in-degree of 0? We see that that is R. Let's go ahead and add it to our output string and remove it from the graph. So we see R here gets removed, R here gets removed, and let's also remove that outgoing edge from R. And now we need to reassign the in-degrees of the nodes that were affected. We see that T doesn't have an incoming directed edge anymore. So now let's go ahead and change that in-degree to 0 because it doesn't have an edge going into it. And let's just restart the process. So let's go find all the nodes that have an in-degree of 0. We see that T has an in-degree of 0 now. Let's go ahead and add it to our output string. And let's remove it from our graph. So T is going to be removed. T is going to be removed here. Let's also remove that outgoing edge. And finally, we need to reassign the in-degrees of the nodes that were affected. F is the only node that doesn't have an edge going into it anymore. So let's change that in-degree from 1 to 0. And finally, last step, we're going to do it one more time. Let's find all the nodes with an in-degree of 0. We see that F has an in-degree of 0. So let's go ahead and add F to our output string. And let's remove it from our graph. And now let's reassign the in-degrees of any nodes that were affected. Now we see that there are no more nodes in our graph. So at this point, we are done with our implementation, and we have an output string of WERTF. And believe it or not, this is the correct output string of this example. So this is very cool. We know that although this is a hard problem, this is actually just a graph problem with a topological sort, nothing that we haven't seen before. Now, before we actually dive into the code, I want to go through a few edge cases that we need to consider. And I'm just going to go to the top right here. I have a few examples picked out. So let's try to represent this as a graph, ZXZ. So in our alien language, they've told us that Z comes before X. Let's just go ahead and add that to our graph. Z is going to point to X. Now, in our alien language, they've also told us that X comes before Z. So, okay, cool. So X comes before Z. But wait, isn't this weird? Z comes before X, but X comes before Z, but Z comes before X, X comes before Z. That looks like a cycle, doesn't it? And this is one of the things that is invalid in any language, and specifically in our alien language, we need to return an empty string when we have a cycle in our graph. So let's just keep that in mind. I'm sure there's a way where we can return an empty string if there is something like that. And also, I want to talk about this example right here. So in this example, let's go ahead and create our graph representation. The aliens have told us that A comes before BCE, and the only reason A comes before BCE is because of this character right here. They differ at the 0th index. So we're going to keep that information in our graph. A comes before B. Now let's look at BCE and BC. Now, this is a weird one because BC and BC here are the same, but we're given this extra E. Now, in the English dictionary, all prefixes come before their actual word with that prefix. So this is actually lexicographically incorrect, and we're going to get thrown an error if we somehow return an output string. So because this is invalid, we need to return an empty string here. So yeah, guys, this is how you do the problem. Very straightforward. Let's just dive into this code, guys. All right, so who's ready for some code? I know I am. So let's see. First things first, I'll usually start the problem talking about what are we even trying to return here? Well, we're going to return a string. Now, if you guys remember from the example that we just saw, we saw that I would append a character to our output string every time we were searching for every time that we were searching for all the nodes with an in degree of 0. So since we're going to append a character one by one, I'm actually going to start with a string builder. And this is much more efficient than a string. I'll make a video about string builders in the future, but right now we're going to use a string builder equals new string builder. There we go. And essentially I'm going to return sb.toString. And this will, give us the string representation of our string builder. All right, so now let's go ahead and figure out how we're going to build our graph. So usually when I'm building a graph, there's a certain implementation that I'll follow where I use a hash map, where the keys will be the nodes and the values will be all the neighbors of that node. So let's do that. Hash map. And what are going to be our nodes in this situation? Well, the nodes will be characters, because we're only going to look at one character at a time. And I'll usually use a list to store all the neighbors of our nodes. So this is a typical graph implementation container that I usually will use for all my graph problems. So a hash map. And while we're here, let's go ahead and create our in degree container. Oops, I spelled graph wrong. So there we go. Let's go ahead and make our in degree container. So our in degree container is also going to be another hash map. So hash map, and remember, an in degree is the number of directed edges going into each node. So what are the nodes that we have in our graph? Well, they are going to be characters, and the number of directed edges going into each node, we can represent that with an integer. So amazing, we have our in degree equals new hash map. And now let's go ahead and initialize each of these. So I'm going to iterate through all of the characters that are in our words input array. So for string s in words, and for character c in s, we are going to put each of these characters into our graph. So graph.put c, and we're going to initialize it with an empty array list. And while we're also here, let's go ahead and initialize our in degree. So in degree, the in degrees of each of the nodes in the very, very beginning, where we actually haven't built our graph, all of our characters that are in our in degree, they're going to have an in degree of 0. So I'm going to do in degree.put c 0. All right, so we've initialized everything here. So I'll even make a comment so you guys can see. Initialize graph in degree. And now let's go ahead and build our graph. So build graph. Now, how did we build our graph? Well, the first thing that we did was we compared each of the words. It's specifically the words that were right next to each other. So we compared WRT, WRF, we compared WRF, ER, we compared ER, ETT, and so on and so forth. So we know we need an initial for loop that will iterate through all of the strings. So I'm just going to say for int I equals 0, I is less than words dot length, I plus plus. Now we always compared each pair, right? So I'm gonna get the first word and the second word, and I'm just gonna hold them in some variables. So string first equals words I, string sec equals words I plus 1. Oh, and that reminds me, since we are accessing I plus 1, to make sure we're not going over the bounds of the length of our words array, we're going to iterate all the way to words.length minus 1. So we don't go over, and that way we don't get any errors. Okay, so now we have our word. And now the way we actually built our graph was we found the first instance between our first and second word where the letters were different, specifically at each index. So when we have WRT and WRF, we iterated till T and F, and we realized that those were different, and that represented a pair of nodes and an edge between T to F. Now, how are we going to do WRF and ER? The first character where they were different was W and E, and we made a directed edge going from W to E. So we need to iterate through each of the characters of our first and second words. Now, to make sure that, once again, let's say we're comparing WRF and ER, where we have words that are two different lengths, right? We don't want to go over the bounds of ER if we're just using WRF's length to iterate through everything. So what we're going to do is find the minimum length between each pair of words. And that will be the constraint that we have when we're iterating through each of the characters. So I'm going to have another variable called int maxlen equals, and I'm actually going to take the minimum of the first word's length and the second word's length. So first.length, sec.length. All right, now we have the max length that we can iterate through. So now I'm just going to iterate through all the characters within each of those words. For int j equals 0, j is less than max len j plus plus. And we're going to iterate through all the characters between the first and second word until we hit a character where they are different at that position. So once again, T and F are different at the second index, W and E are different at the 0th index, R and T are different at the first index. So we're just going to iterate till we find two characters that aren't the same. So if first.car at j does not equal sec.car at j, that means we found the first pair of nodes that we can add to our graph, and we have a directed edge going from the first word going to the second word. So let's add this information into our graph. Now the first thing that we're going to need to do is grab all of the current neighbors of this particular node. Since we have a list of characters as our value, we want to add the character in the second word into the list of the first word. And essentially, we're just adding to a list of all the things that the first character is pointing to. So that might have sounded a little confusing, but I think when you guys see the code, you'll understand a little bit better. So let's go ahead and grab all the characters that the first node is pointing to. List character, and I'll just call this like neighbor equals graph.get first.char at j. So now we have everything that this character is pointing to. And now what we're going to want to do is add this character, the character at the second word, into the neighbors list that we had just received. So neighbors.add sec.car at j. By doing this, we are making a direct connection between the first word and the second word. We're basically saying that the character in the first word is pointing directly to the character in the second word. That's what's happening when we have these statements right here. And finally, we're going to put this information back into our graph. So graph.put first.char at j neighbors. We're just updating the neighbors of our first .car at j, and we're just going to put it back into our graph. And while we're here, since we're essentially making a directed edge from the first.char at j to the second.char at j, let's change the in degree of the node that was affected. And in this case, it's the in degree of the second.char at j. So let's do indeg.put second.char at j. And what we can do is get the current in degree of that character. So in degree.get second.car at j. And we can just increment that in degree by 1 plus 1. All right, very cool. So after this, we don't want to iterate through any more of the letters of each of the words. And we do this because it even tells us a string S is lexicographically smaller than a string T if at the first letter where they differ, the letter S comes before letter T. So we don't really care about any of the letters after that. So let's just break out of this for loop once we're done with that. All right, so now we have built our graph, and now we can start our topological sort algorithm. So let's start topological sort here. And for our implementation of topological sort, we need a queue. So let's get a queue, and this queue is going to hold the nodes of our graph. So in this case, it's going to hold the character class. And I'm just going to call queue. Oops. Oh my God. Equals queue. Queue equals new linked list, like that. And now let's ask the question. What exactly gets inserted into our queue? We need to find all of the nodes in our graph that have an in degree of 0. So let's just do that. Let's iterate through all of the nodes of our graph. So how do we do that? We can say for character node in the graph.keyset. This will iterate through all of the nodes that are in our graph. So if the in-degree of the node, so in-degree.getNode equals 0, we have essentially found a starting point for our topological sort. And hence, we can add this information to our queue. So queue.add node. And after we remove the node from the graph, we are going to iterate through all the nodes one more time and see if any of the nodes in degree is 0. And if that is the case, we're just going to add that new node into our queue again. So essentially, we're going to say while the queue isn't empty, the first thing we're going to do is pop off the first node in our queue. So character C equals queue.pull. Now remember, and by doing this line, we are essentially removing it from our graph. Like this is us saying that we're going to remove this node from our graph. And remember, every time we remove a node from the graph, we're going to add it to our output string. So this is where the string builder that we've created at the very top, this is where that's going to come into use. So sb.append C. Okay, and now after this, since we're removing it from the graph, we need to reassign the in-degrees of all the nodes that were affected. So what I'm going to do here is grab the neighbors of this node. So list character neighbor equals graph.getC. And we are going to go through all the neighbors first. So for character n in neighbor, the first thing that we have to do here is reassign all the in-degrees. So for all the neighbors of this node that we had just taken out, let's decrement the in-degree of those nodes. So what I'm going to do here is indeg.put n, and I'm going to decrement the in-degree of each of the nodes. So indeg.get n minus 1. And notice what we're doing here. We're essentially taking all the neighbors that this character pointed to, and since we removed this from the graph and removed that edge from the graph, we've removed a directed edge going into this node, this neighbor here. So that's why we're reducing the in-degree of that neighbor by 1. Now, after we go through all of our neighbors and decrement the in-degree, let's do a quick check to see if the in-degree of that node is 0. N equals 0. And if it is, we're going to put that node into the queue. So queue.add n. And after this, this bit of code right here is all we have to do for our topological sort. And since we just keep appending the new characters to our string, we've essentially done our topological sort. So it's not as bad as it looks. It might have looked a little intimidating when we were going through the example, but this is actually not too bad at all. And now we're essentially done. So let's just run this. Make sure I didn't make any.
They ask you how you are, you just have to say that you're fine.
Of course I did. So for character C and S. Oh, okay, so this is my bad here. We can't actually access each individual character in the string, but we can access each individual character in the string.toChar array. This is a really cool method that takes every character of the string and puts it into a character array. So hopefully that'll do it.
You're not really fine, but you just can't get into it because they would never run.
Okay, and we made another mistake. All right, so indeg.get second. Oh my goodness. I didn't call it second. I'm sorry, guys. A little mistake here. Hopefully this is it. No more mistakes. All right, so we passed the initial test. All right, great. Now there are a few things that we're missing here. All right, so even though we have this test working, there are some cases that we haven't checked that I mentioned earlier in our other example. So it tells us if there is no solution, return an empty string. So one thing that we can check is, remember I told you guys that prefixes have to come before words that contain that prefix. If it's the other way around, where let's say we had the word an, and then so an would be a prefix of ant, right? So this is legal. We're good here. But now let's say we had ants and then an. this is illegal. We cannot have this. So essentially, if our second word is a prefix of the first word, then this is illegal, that the language is illegal, this alien dictionary is invalid, and we have to return an empty string. So let's see, where is the first time I access the first and second? Okay, it looks like right here. So what we're going to do here is we're going to do a few quick checks. What we'll do is check to see if the length of the first word is greater than the second one. See, that should be the first big flag. Okay, so if first.length is greater than sec.length, okay, and obviously we don't want to flag every single pair where the first word is greater than the second word. We also need to make sure that the second word is a prefix of the first word. And we can do this with the substring method. So if the first length is greater than the second length, and if the first.substring 0 to max len, because remember max len would be like the minimum length of both strings. So if the first.substring max len dot equals the second word, then we need to return a empty string. We can run a quick check here. Let's see WR and WRT and WR. Let's see if this returns the empty string. Yep, look at that. Returns the empty string. Perfect. This is exactly what we wanted. And now the final thing is if we have a cycle in our dictionary, then we to return an empty string. Now, I addressed this in my course schedule 2 video, so you guys if you guys haven't seen it, I really, I want you guys to go look at that. I really go in depth there. But a quick cycle check technique that we can use when we're doing topological sorting is make sure that our string that we're returning has the same number of characters that were in our graph. So since we're looking to make sure that the output string contains all the characters that are in our graph, a very simple check we can make at the very end is if sb.length does not equal our ndegree.size, we can also do graph.size, it's all the same here, return an empty string. And this should solve the problem. So now we've written all our code for the topological sort, we've taken care of our edge cases, I think we're done here. So let's go ahead and submit this. Perfect. 3 milliseconds faster than 87%. Now, I do want to warn you guys, I think, I've used the same, example, same code for multiple attempts here. And sometimes you'll get 87. Right now, for whatever reason, I'm getting 87. But when I used the same code earlier before, I was getting 7 milliseconds, 6 milliseconds. So just keep that in mind. I don't want to skew you guys in the wrong direction by this. But this is pretty good. Space complexity. So here we're iterating through all of the characters in each of the words. So immediately we have an O of NM situation where N is the number of words and M is the number of characters in each word. So we can further simplify this to like O of N, where N is the number of characters that we're iterating through. And since we iterate through this one time, then now we go through this double for loop where this time we're not iterating through all of the characters like we did before. We're just going through like the min of each pair of words. So let's say at the worst case, each of the words in our input array were like the same number of letters. Then we would have like an O of M times N once again, like we had up here. So it would just be O of like the number of characters, worst case. And finally, topological sort, one of the beauties of topological sort is it actually happens in linear time. Linear where you take into consideration all of the vertices and edges. So it would be O of V plus E here. But like, I think, iterating through all of the characters up here is much heavier in terms of time complexity compared to the topological sort. So I will say overall time complexity is O of N times N, where N is the number of words and M is the number of characters. And now space complexity, most of the space really is held in our hash maps. So in the worst case situation, we would basically have each of the alphabets in our words. So let's just say each word was each of the characters of the alphabet. So we had A, then B, C, all the way to Z. Then we would have a max of 26 words. And guys, here's where I am actually a little uncertain, because if the max amount of words we can have is 26, in the worst case, we would have O of 26 storage here. Where in our graph, we'd have 26, in our integer, we'd have 26 elements. So I want to say that storage is O of 26, which would actually become O of 1 constant time. But I would, love for you guys to tell me that I'm wrong with this. I'm actually not 100% sure about, the storage, but I feel like if at the worst case you can have every single letter in there, there's 26 letters total, so maybe I think that makes sense. But let me know if you guys think differently. Guys, I learn as much as you guys making these videos, and if I am not 100% sure, I don't want to give you guys wrong information. So if you guys have a great explanation for the space complexity here, I will pin that comment at the very top. But yeah, guys, that's how you do this problem. I really hope this made sense. This is a very, very tricky one, and it definitely took a little time, but I think once you start doing a few graph problems, such as course schedule 2, there was like a few bipartite problems that are really good. I'll link everything in the description, but once you do a few graph problems, you realize that all of them are very, very, very similar. And when I saw this one and I realized that this was a topological sort algorithm, this code is actually super similar to my course schedule 2 code, and honestly the course schedule 2 problem. So once you do a few of them, you'll notice a lot of big patterns with the graph problems, because there's only so many types of graph problems that you could be asked in an interview setting. So yeah, I really hope this was helpful. If you guys found any value from this video, you guys just go ahead and give this video a big like, subscribe to the channel, comment down below the next problem I should do. And yeah, guys, I really hope you have a great rest of the day, and I'll see you guys next time.